that's worked example 2 on page 20. So you can see here that we have been given the mass of the hydrated salt, the mass of the anhydrous salt, and from that we can work out the mass of water. So this is actually the structure of how we're going to do each of the examples from this point on. We're going to get the mass of the hydrated salt, the mass of the anhydrous salt, work out the mass of water, and then get our ratio from that. Okay, so you can see here in the question, let me just highlight where we got that. So we've got 4 grams of the hydrated, okay, and that's written here. Produces 2.56 grams of the anhydrous copper sulfate. Okay, the difference between those two is going to be your mass of water. So that's what we'll always do: the hydrated, the anhydrous, and then we'll work out the mass of water. Okay, so the anhydrous salt in this case is copper sulfate, CuSO4. The water then obviously has the formula H2O. Okay, no problem. The mass of the anhydrous salt is 2.56. The mass of the water is 1.44 grams. Okay, what we're going to need to do, we don't need a mass ratio, but we need a moles ratio. In order to convert to moles, I'm going to need my RFM. Okay, I'm going to need my RFM. So we need to work out our Rfm of copper sulfate first of all. Okay, so follow along with me in your periodic table and your calculator if you can. So I'll just do it up here first of all. So CuSO4. How many coppers do we have? 1. And what's the mass of copper? 64. What about sulfur? Yep, there's one of them and has a mass of 32. Oxygen then? 16 times 4. Add that all up in your calculator and you should get 160. So that's your Rfm of copper sulfate. What about the Rfm of water? Can you remember it? Yeah, it's 18. It's worth just learning that. Okay, then how do we work out moles? Good. N equals mass over Rfm. Okay, so for copper sulfate, that's 2.56, your mass, over Rfm, 160. Pop that into your calculator and you should get 0.016. For water, it's going to be 1.44 divided by 18, which should come out as 0.08. Okay, what I want now is a mole ratio in whole numbers. How do I do that? Good job. Okay, so we divide by the smallest number. Which is the smallest number in this case? So 0.016 is our smaller number of moles, and what you'll find is that it's always the number of moles of the anhydrous salt that is the smaller number, because there's always a number in front of water, maybe anything from 1 to 10. So anhydrous salt will always work out as your smallest number of moles. So when we divide that through, we end up with a ratio of 1. Then 0.08 divided by 0.16 is 5. So we end up with a ratio of 1 to 5. So we can see now that our formula of copper sulfate is CuSO4.5H2O, because anhydrous salt and water are in the ratio 1 to 5. So now you can continue on with exercise 4, completing these questions. So this is exercise 4, if you want to take a title in your blue book. And it's question number 1. Yes, yeah, bottom's right here. Okay. So you're told in this question that you have 5.643 grams of hydrated copper chloride. So what I would like you to write essentially is just really abbreviate it down. You want to get the mass of the hydrated, the mass of the anhydrous, and then the mass of the water. So what's the mass of your hydrated salt? Good, 5.643 grams. What about your anhydrous then? What's the mass of your Good, just from the question, 4.455 grams. How do I then get the water? Yeah, it's a difference between the two. The rest is made up of water. So you just do 5.643 minus 4.455. Okay, what do you get that to come out as? Good, 1.188 grams. Okay, at this point I'm then just putting them in the ratio of the anhydrous to the water, the anhydrous salt to the water. Okay, it's copper chloride, CuCl2 to your water. A couple of things I need to write down first of all are your mass and your RFM. So I've just worked out the mass of the anhydrous is 4.455. It's always the anhydrous one. 4.455 grams, and the mass of water is 1.188 grams. Okay, need to work out your RFM of copper chloride. So again, you're looking at your relative atomic masses. What's the relative atomic mass of copper? 64. And then you've got two chlorines, each with a mass of 35.5. If you put that into your calculator, it should come out as 135. So your RFM is 135, and of water, 18. Okay, what do I need to do at this stage? Yeah, find the moles. So I do N equals mass over RFM. Okay, so for copper chloride, that's going to be 4.455 over 135. What does that come out as? 0.033. And for water, it's 1.188 over 18, which is 0.066. Next step, divide through by your smallest number of moles. In this case, and will be in every case, will be the mass or the moles of your anhydrous salt. So you're dividing by 0.033. Both numbers by that. What ratio does that give you? 1 to 2. Okay, so you can write your formula simply as CuCl2 dot 2H2O. Okay, and the question actually asks you what is the value of X, so you would simply write X is equal to 2. X is the number of waters. So I'm just going to give you the answers to exercise 4 so that when you're doing them at home, you know if you're getting the right answer. So exercise 4, calculating the degree of hydration. Number 1, it works out that your ratio is 1 to 2, so X is equal to 2 waters of crystallization. Number 2, it asks for the full formula, so you need to write it as BaCl2 dot 2H2O, again a ratio of 1 to 2. Number 3 works out as a ratio of 1 to 1. Li2SO4 dot H2O. Number 4, it works out that N, the number of waters, is 9. Doesn't matter whether it's N or X, they're still representing the number of water. Number 5 is X is equal to 10, your ratio is 1 to 10. Number 6 is different. If you can't get it, don't worry too much about it. But essentially you need to remember that when you heat your hydrated salt, it will form the anhydrous salt and 6 waters. So if you work out the number of moles of your hydrated salt by doing N equals mass over RFM, because you're given the mass and you can calculate the RFM because you know that there's 6 waters, and then you bring that over here, it's in a 1 to 1 ratio, and then you can use mass equals N times RFM of your anhydrous salt to get the mass of it. So that is slightly different for number 6. Number 7, then the final question in this exercise, X is equal to 10. So starting on page 22, we are looking at the concentration of solutions and doing calculations for that. These are actually very straightforward. It's a simple equation that you need to use, but it's just making sure the key thing is actually about units. A bit like last year when we looked at the equation N equals mass over RFM, what did we have to be careful about our mass? Had to be in grams. So, for example, if it was given to you in kilograms or in tons, you had to convert it to grams first. It's a bit like that with these calculations as well. So what we're doing is we're going to be able to work out the concentration of solutions. We looked at this last year when we looked at acids, saying that the higher the concentration is, obviously the stronger that the acid is. Concentration by definition is the number of moles of a substance dissolved in 1 decimeter cubed of solution. 1 decimeter cubed is just the metric unit for volume, and it's equivalent to a litre. Okay, you don't need to worry too much about that, but just to give you an idea of what size that would be, 1 decimeter cubed is a litre. So if you buy a 2 litre bottle of Coke, you could say that's a 2 decimeter cubed bottle of Coke if you wanted. Okay, this is the key thing you have to be careful of, because last year we learned that concentration was in moles per decimeter cubed, which fits the definition, the number of moles in 1 decimeter cubed. But sometimes you are given the volume in centimetres cubed, and so you need to know how to convert. If you're given it in centimetres cubed, you need to divide by 1,000, okay? You need to divide by 1,000. 1 decimeter cubed is equal to a litre. Decimeter is a decimeter is a decade is 10, isn't it? No, yeah, so it's 10 centimeters or a tenth of. It is. Let me think, because a centimeter cubed. Yeah, it's 10 centimetres. Okay, so 1 decimeter is 10 centimetres.
So 1 decimeter is 10 centimetres?
Yeah, okay, so that means 1 decimeter cubed is 10 times 10 times 10, which is 1,000 centimetres cubed. Yeah, that's how we work that out. Okay, you're testing my memory there. Okay, so what we have here is an equation then for concentration. If it's moles per litre, then it is moles divided by the volume in decimeters cubed. Okay, so we've got a triangle here, a bit like we had last year, and from that we can get 3 equations. Okay, your units are really important. For number of moles, it's MOL. For concentration, it's moles per decimeter cubed, and for volume, it is decimeter cubed. If you're given it in centimeters cubed, you must first convert by dividing by 1,000. Okay, so let's see what 3 equations we can get from this triangle. So first of all, if I cover N, what am I left with? C and V. So N, which is the number of moles, is equal to concentration times volume. N equals CV, concentration times volume. If I was asked to get the concentration, what would it be? So number of moles divided by volume. Again, that volume must be in decimeters cubed, not centimeters cubed. And then finally, V, volume, is equal to number of moles over concentration. See, these first 2, they would be the most common ones you have to use, so I would have those in your head. N equals CV and C equals N over V. The first step is to choose the correct equation. Okay, so the question asks me, find the concentration of a solution that has 10 moles of solute dissolved in 4 decimeters cubed. First step is to work or to pick your equation. Okay, so which equation am I going to use? C equals N over V. Okay, we've got to check our units here. So number of moles, how many moles do I have? 10. Okay. Volume. What unit must volume be in? Say again? Decimeters cubed. Yeah, must be in decimeters cubed. Which it already is, so I don't need to convert that. Okay. So when I'm working out concentration, I'm doing N over V, which is simply 10 10 moles over 4 decimeters cubed. Put that into your calculator. Is 2.5, and then your units of concentration, if you've put them in the correct units, is moles slash decimeter cubed. Moles per decimeter cubed. And it literally means in that solution you have 2.5 moles dissolved in every 1 decimeter cubed, which is the same as 2.5 moles in a litre. Okay, next example incorporates that idea of us having to convert units. Okay, so it says find the concentration. So before I move on, what equation am I using? C equals N over V. But again, just to keep myself right, I am writing out what my number of moles is, and I'm writing out my volume. Okay, so what is your number of moles? 0.2 moles. And your volume has been given to you as 100 centimetres cubed. But what's the problem here? It's not the right unit. How do I convert to decimeter cubed? Divide by 1,000. Okay. And that should give me 0.1 decimeter cubed. 1 centimetre cubed is actually equal to a milliliter. So it's the same conversion here. There would be 1,000 millilitres in a litre. So there's 1,000 centimetres cubed in a decimeter cubed. Okay, now I'm ready to put it into my equation. C is now 0.2 moles over 0.1 decimeter cubed. And that comes out as exactly 2. And your units are moles slash decimeter cubed. Okay, so let's go back to page 23, which is and worked example 3, and we're asked to calculate the number of moles this time. So first thing, pick your equation. What is the equation for number of moles?
C times V.
N equals C times V. Okay, N equals CV. Okay, so C is your concentration, which you've been given as 1.5 moles per decimeter cubed. Your volume is 25 centimetres cubed. Okay, but that's a problem because when I multiply these together, essentially I want my units of volume to cancel out. They're not going to do that if one is centimetres cubed and one is decimetres cubed. So I've got to convert that to decimetres cubed. How do I do that? Divide by 1,000 and you should get 0.025 decimetres cubed. Okay, now it's time to put it into your equation. It's all ready to go. So N equals CV. Now that my units match up, it is simply 1.5 times 0.025. And that should come out as... Don't have that. Yeah, 0.0375 MOL. Okay, so that's just simply using a rearrangement of the equation. Okay, is that all okay? Again, making sure that you have your units of volume in decimeters cubed is the key thing. Okay, over then worked example 4. Now worked example 4 is a little bit different, so I'll ask you to focus carefully on this one. You may be given, instead of the number of moles in a particular volume, you may be given a mass, okay? But you know that the units of concentration is moles per decimeter cube. So I've got to work out the number of moles per decimeter cube. The linking factor with these will always be the number of moles, okay? And that will make sense as you're doing these calculations. But if I've been given a mass of solute, I've got to convert that to moles first. How would I do that? If I've been given a mass and I want to work out the number of moles. Go for it, Neve. Good. N equals mass over Rfm. So there's actually 2 steps to this one. So these are the slightly more tricky ones. Okay. So we've been given here the concentration of sulfuric acid if 49 grams is dissolved in 2 decimeters cubed. So the first thing I need to do is work out the number of moles. Okay. So use my equation, N equals mass over Rfm. My mass, what do I have to check it's in? Grams, which it is, so we're fine. Rfm then. Okay, and we need to work that out of sulfuric acid. So I take each of my atoms, I look at how many they are, and I multiply by the atomic mass. So hydrogen, first of all, I've got 2. What's its mass? 2 times. Yeah, I've got 2 hydrogens and each with a mass of 1. Okay, because it's H2SO4. Okay. Sulfurs, how many do I have? Well, I just have 1, but it has a mass of 32. Absolutely. Okay. And then oxygens, 4 multiplied by your mass, which is 16. Put that all into your calculator and you should get 98. Perfect. Okay, so let's work out our moles. N equals mass over Rfm. So it's going to be N equals 49 over 98. 0.5 moles. Perfect. So now that I've got N, I can work out the concentration. Because the 2 things I needed for concentration was N and V. So I had to work out N first of all. So C is equal to, can you remember the equation? N over V. N I've just worked out is 0.5 moles. Volume, what do I need to check it's in? Decimeters cubed. So it's 2 decimeters cubed. So concentration is simply 0.5 moles over 2 decimeters cubed, which is, should be able to do that in our head even. Okay. 0.25, I'm halving it. 0.25 moles per decimeter cubed. Okay, example 5 is the same, but just working backwards to actually get the mass of the solute. Okay, so stick with me as we do example 5. I'll keep that up at the top in case anybody is still working. Okay, so the question here is what mass of sodium carbonate would be needed to make 500 centimeters cubed with a concentration of 0.8 moles per decimeter cubed. Okay, so the link is always N. So if you're looking, okay, well, I'm not used to concentration and mass equation. That's because there's not one that directly links concentration and mass. So you've got to work out the number of moles first. So you can see in worked example 4, the thing I worked out first was the number of moles before I continued on. Again, here, we're working out the number of moles before we move on. Okay, this time I'm working the other way around. Okay, so I use N equals CV to get the number of moles that I require. Okay, so what is your concentration? 0.8 moles per decimeter cubed. Your volume, because it's 500 centimeters cubed, but I can't have my volume in centimeters cubed. I need it in decimeters cubed, which is 0.5. Okay, put that into your equation. N equals CV. So it's 0.8 times 0.5. What's that come out as? 0.4. Good. 0.4 moles. Because you're multiplying by a half, essentially. No, because 8 times 5 would be 40, which is why, because I know you're thinking of the 2 decimal place thing. But because it's 40, it then moves up. Okay, so you're doing 0.8 times a half, essentially. So half of 0.8 is 0.4. Put it into your calculator, it'll come out like that anyway. Okay, but go back to the question, and it asks you what mass of sodium carbonate would be needed. So I'm not interested in the number of moles, I'm interested in the mass. So I need to use the equation mass equals N times Rfm. Okay? Okay? Number of moles I've just worked out is 0.4 moles. Rfm of sodium carbonate. Now they give you the formula here. So I just need to work out the Rfm from my periodic table. So how many sodiums do I have? 2, each with a mass of 23. Carbons? 1, each with a mass of 12. Okay, and then oxygens, 3, multiplied that by their mass, which is 16, yes, and the total RFM then is 106. Okay, last step is then just to put that into your calculation, into your equation. Mass equals N times RFM. So 0.4 times by 106. Good. 42.4, and you're absolutely right. My units, if I've put it in correctly, should come out as grams. If it was an extremely large number, you could divide by 1,000 and turn it into kilograms. Okay, so those ones are the slightly more tricky ones where you have to use both equations. Have a go now at exercise number 5. Question 1 is simply just calculating the concentration. So it's going to be using worked example 1 and 2. So worked example 1 and 2 for question 1. You're simply going to be using the equation C equals NV, but what I would say is check your units each time. Remember that volume has to be in decimeters cubed, so for the likes of part B, you must convert your centimeters cubed into decimeters cubed first. For question 2, those are the slightly harder calculations where you have to use both equations. You're asked to calculate the concentration in moles per decimeter cubed, but you're not given the number of moles, so you must work that out from the mass. So for all of question 2, what you'll be doing is working out your moles first, N equals mass over RFM. And then the second step will be working your concentration by doing C equals N from the value you've just calculated divided by V, your volume. Again, check your units, particularly in B and C. Number 3 is doing a similar thing, but the other way around. And then question 4 and 5 are simply calculating the moles using N equals CV. So have a go at that now. On page 27, we look at this idea of atom economy. Okay, sounds a little bit strange, but back in year 11, you worked out something called percentage yield, which was able to tell us how efficient a reaction was in terms of the amount of product that we got. This is a little bit different. It's actually essentially working out the efficiency of a reaction, but according to the atoms. It's working out what percentage of the atoms of your reactants are incorporated into a useful product. Okay, so what it's saying here is that in a reaction, the reason why we balance equations is that all atoms in the reactants are incorporated into the products. And what we are going to do is work out, well, how many of those atoms are incorporated into useful products. So let's have a look at this example halfway down the page of glucose. Glucose, when it undergoes fermentation, you will know that it produces ethanol and it produces carbon dioxide. Which do you think is your useful product there? The ethanol, okay? But not 100% of your atoms are converted into ethanol. Some of them escape off as carbon dioxides. And what these calculations will allow us to do is to be able to work out how efficient the reaction is in terms of the atoms. You need to know this expression. This would be potentially worth 2 marks if they asked you just to quote a definition. In fact, if you were asked for a definition of atom economy, this is what your definition is. I know it's an equation, but that's what the definition would be. So it is essentially the percentage of the atoms that are incorporated into the desired products. So it's the RFM of the atoms in the desired products over the total RFM of the products and times by 100%. Probably best looked at with an example. So if you turn over to page 27, okay, we're going to have a look at that reaction of glucose undergoing fermentation to ethanol and carbon dioxide. What you need to do is work out the RFM of your useful products, work out the total RFM of your products, and then work it out as a percentage. It's actually really, really straightforward. Okay. How you work out which is useful, it actually will tell you in the question, not explicitly as the useful product is, but can you see here that it says calculate the atom economy when ethanol is made. When ethanol is made, that means that it's ethanol is our useful product. Okay, so it will actually tell you in the question, not explicitly like ethanol is a useful product, but it'll be the one that it mentions is being formed. Okay, so ethanol is your useful product here. Okay, so the RFM of your useful product, first of all. Okay, so my useful product is ethanol, but how many ethanols do I have? 2. So I actually need to multiply it by 2. Okay, so I'm going to write in here, my useful product is 2 times C2H5OH. I'm going to keep the 2 out of it for now, because normally we don't include balancing numbers with RFM. Okay, so I'll keep that on the outside and I'll do my working out on the inside of this. Okay, so let's work out the RFM of ethanol. How many carbons do you have? So it's 2 times 12, which is the relative atomic mass of carbon. How many hydrogens? And be careful about this. There's actually 6. So if you look here, there's 5, plus this one is 6. So 5 plus 1 is a total of 6 hydrogens. What's the mass of hydrogen? 1. Okay, and then what am I adding on? 16, because I have 1 oxygen. Okay, so what's the relative atomic mass of ethanol as such? Ignore the 2 times that. Say again? Not quite. Try that again. Yeah, so ignore the of ethanol just so that what's in this square bracket. Yeah, 46. So 2 times 46, which is then 92. So let me be clear, the RFM of ethanol is 46, but I have 2 ethanols, so I need to multiply it by 2. Okay, total RFM of the products then. Okay, I know I'm a little bit underneath this here, but this is the working out for the total RFM of your products.
What if you did like, say that it's like C2H5, you can change up to like C4.
Yeah, when you're working out the RFM, absolutely, you can multiply it 3 first of all. That's absolutely fine. Okay, so total RFM of the products, what you have is you have 2 ethanols and you have 2 carbon dioxides. I've actually just worked out the mass of 2 ethanols. What was it? Yeah, I've actually just done this calculation. You can do it again if you want, but there's no real point. So you can just put that in as 92. And then I've got to do my 2 carbon dioxides. So I've got 2 multiplied by, how many carbons do you have? 1, which has a mass of 12. And then you've got 2 oxygens, each with a mass of 16. Okay, so it's going to be 92 plus 2 times by 44. Perfect. Okay, which is going to work out then as 92 plus 88. And what does that come out as? 180. Okay, so you're just totaling up the RFM of all your products at that point. Okay, so sorry, I know I'm running a little bit underneath my working out. Atom economy then, you need to learn this equation. Okay, it's different from percentage yield. Go back to your previous page. It's the RFM of your useful product over the total RFM of your products, and then times by 100% to make it a percentage. Okay, so I would just abbreviate this as, I'll maybe do it off to the side here in different colours so you can see it. So AE, atom economy, is going to equal your RFM of your useful product, which is 92, over the RFM of the total RFM of your products, and then times by 100%. Percentage yield is something completely different. I'll come back to that afterwards. It was something from year 11. Well, technically it could come up because it would be what they call synoptic knowledge. It's something you've learnt before. They could slip it in there, but it's not specifically on your Year 12 course as such. And there's so much in this topic that I would doubt that they would add something else in, but you just never know. Okay, just put that into your calculator. What does the workout as? Good. Okay, I would normally do your percentages to 1 decimal place. So 51.1%. Okay, yeah, sorry, I missed that, but that is the same.
Does that mean like 3 figures or like 3 after the...
No, it means 3 significant figures, so it depends whether, if it was to come out as like 0.05156778 or something like that, these are not significant, the zeros before your number starts. Okay, so it would be 0.0516.
But does it mean 3 significant figures?
So worked example 2, we need to find the RFM of the useful product first of all. We'll get to the stage where we'll just abbreviate that as UP, for example. Okay, RFM of the useful product. Okay, so our useful product, it says calculate the atom economy for the addition of bromine to cyclohexane. Okay, how do I work out in this case what the useful product is?
It says it's dibromocyclohexane.
Okay, so it's a product, so it has to be on the right hand side of the arrow. So it is my dibromocyclohexane. How do I know that's the useful product?
That's the only product. That's the only product.
It's the only product. Okay, so I've only got one of it, so it's C6H10Br2. Okay, stick with me. So I need to work out the RFM of this. All right, try and do this yourself. Have a look at your periodic table. Okay, give that a wee go yourself before I go through it. Working out the RFM of dibromocyclohexane. Pardon? Okay, have we all given this a go? I probably couldn't do the adding up, but I can do the RFMs. So, okay, Year 12, stick with me please. So it's 6 times 12 plus 10 times 1 plus 2 times 80, isn't it?
Yeah.
Okay. And that should come out as 242. Okay. Total RFM of the products then. Okay, it's just your C6H10Br2 because that's the only product. So it's also 242. Okay. So remember then that the percentage atom economy is the useful product over the total RFM of the products. So that's going to be 242 for your useful over 242 for your total RFM of the products times by 100%. What does that come out as? 100%. Okay. So listen up please. This is actually a really important point that we can learn from our atom economy. In reactions where there is only one product, the atom economy will always be 100% because what has happened is all the atoms have been incorporated into that one product. So if there's only one product of a reaction, it's actually the most efficient or economical atom-wise. It might not be a 100% yield, so it might not fully convert to that. But in terms of atoms, they are all put into that one product rather than any escaping off as a side product. Okay, so the last question looks at that joyous thing of the blast furnace, which hopefully you will remember. Okay, yeah, absolutely. So it's where we extract iron. Okay, so what we're going to need is we're going to need the RFM of our useful product and we're going to need the total RFM of our products. So I actually think it's a little bit easier. Our sums were getting a bit complicated there. Is to actually think, well, what's the RFM of iron what's the RFM of carbon dioxide, and then go from there in our calculations. So this time, read the question again. So it's about reading the question and working out what's your useful product. So it says, in the blast furnace, carbon monoxide is used to reduce iron oxide to iron. What do I want to produce in the blast furnace? Iron. So it is your useful product. You can abbreviate that as UP. Okay, I don't use the blast furnace, a really expensive process, to produce carbon dioxide, which I could make by burning some coal. Okay, it'll be the one that's mentioned in the question. Okay, so what I'll end up needing is the RFM of each of these things. So I'm going to do that first of all. So what is the RFM of iron? And what I mean by that is 1 iron. So Fe. Yeah, 56. Okay, and then the RFM of 1 molecule of carbon dioxide. Okay, so I've got 1 carbon, so that's 12. And then I've got 2 oxygens, which is 2 times 16. So what's the RFM of it? 44. Okay, I think that's just a little bit easier to do at this stage, because then it eliminates the square brackets and the circular brackets and all that. Okay, so but then set out your working out RFM of your useful product. Are you happy for me to abbreviate that to UP? UP is just useful product. Okay, we've got 2 iron, so it's 2 times the RFM of iron. We just worked out that iron has an RFM of 56, so it's 2 times 56, which is 112. What do I need to work out now? The total RFM of the products. Okay, for your total RFM of the products, you need to do 2 times iron plus what? What's your other product? 3 carbon dioxides. Okay, so this is why it's helpful to have those RFMs worked out before, but you need to remember that you don't include the balancing numbers in the RFM, or whatever you do, you need to just do that once essentially. Okay, so 2 times iron is 2 times your 56, plus 3 carbon dioxides is 3 times 44. Put that into your calculator. Should come out as 244. Okay, and then finally you work out your atom economy by doing the RFM of your useful product over the total RFM of your products. So that's 112. Maybe color code this. Do 112 over 244 times by 100%. Say that again? Yeah, absolutely. Okay, so if they don't state how many decimal places to do it to, I would go for 1 decimal place, or that idea of 3 significant figures, whatever you find easiest to get your head around. So it goes to 45.9. Okay, and the very last bit of this topic is just talking about what does atom economy actually mean. So and why are we considering it now? Previously we would have just looked at percentage yield, so how much product am I actually getting out, how efficient is my reaction, but it's really an area of chemistry called green chemistry, and that's looking at environmental chemistry and looking at how we can incorporate as much of our reactants into useful products as possible. It goes without saying that the higher the percentage, the better the atom economy, and that is more useful essentially. We're converting more of our reactants into useful products, and there's less that is being produced as waste. Okay, so you can see that reaction in the blast furnace, only 45.9% of our atoms are converted into useful products. The rest of that is converted into products that we don't actually use. Carbon dioxide, which actually is a hassle to get rid of and harmful to the environment. So actually quite a big drive of green chemistry at the minute is developing reactions which are producing less waste products, which gives you a higher atom economy, which means that more of your reactants are being converted into useful products. More of the atoms are being used in those useful products. So in terms, that has benefits of economic reasons and also environmental reasons as well. So the main thing is, the higher the atom economy, the better, both in terms of environmental chemistry and in terms of economics as well. Obviously, you're wasting less money dealing with waste products that you don't actually need. Finally, I just want to give you the answers to exercise 6. Your atom economy questions, so that you know that you're doing them correctly. So question number 1 should work out as 62.9%. Number 2 should work out as 56%. Number 3, 52.9%. Number 4 is 53.8%. Number 5 is 74.4%, which is answer C of the multiple choice. Number 6 is 77.7%. And then finally question 7 is just essentially your definition from page 27.